In this video, we'll look at a very important concept known as cuttings. Consider a set of n lines in a plane. A 1/r cutting is a set of triangles that have the two important properties. First, they have to cover the entire plane. And second, every triangle in the cutting should be intersected by at most n/r lines. The size of a cutting is the number of triangles used in it. For example, in the picture, every triangle is intersected by 3 lines. Note that since we require the cutting to cover the entire plane, we allow some triangles to be infinite. As you can see in the picture, this triangle is in fact an infinite triangle. The main theorem here is that for any set of n lines and any parameter r, we can find a cutting of size roughly r squared. Here we will prove this theorem, but a slightly weaker version of it. In other words, we will not prove an r squared bound, but we will prove slightly larger size. The proof technique that we use here, it's very general and it's very useful. And because of its generality, it's very important that we see this proof, even though later we'll see a better proof of this cutting lemma. Consider a set of lines P. We pick a parameter P, small p, and then we sample every line independently and with probability P. Let's S be the set of sampled lines that we obtain. We look at the arrangement created by a set of lines in S, and then we triangulate every face that is not a triangle. For example, this face is not a triangle, so we add these extra line segments, and then we create 3 triangles inside. By repeating this operation inside every face that is not a triangle, we obtain a number of triangles. The triangles obtained in this way will be the triangles that we use in our cutting. First, it's obvious that these triangles cover the entire plane. Thus, it remains to prove the 2 other important properties of a cutting. First, we have to prove that each triangle obtained in this way does not cross many lines. And second, we have to prove that the number of triangles we obtain here is not too many. First, let's look at the number of triangles that we obtained. Since we sample each line independently and with probability P, the expected number of lines in our sample will be n times P. Using Markov inequality, it follows that the probability that the set S contains more than 5 times the expected value, or 5 times Pn lines, is at most 1/5. You can think of it this way. NP is the average number of lines that we'll see in S. So if S contains more than NP lines, more than 5 times NP lines, with probability more than 1/5, then it follows that the average number of lines in S should be more than n times P, which is a contradiction. So therefore, we must have that this probability is at most 1/5. This is considered bad event, so that's why this is drawn in red. With probability 4/5, this bad event, or this bad event of having too many lines, does not happen. In other words, the probability at least 4/5, we will create at most 5 times NP lines, and therefore by triangulating we'll create an order of n squared p squared triangles. Let's keep this in mind. Now consider triangle in the original arrangement. The vertices of this triangle are the same as vertices of the arrangement created by lines in P. We say this triangle is illegal if it crosses more than n/r lines of P. It is obvious that for our cutting to be a valid cutting, we should have no illegal triangles. So let's look at the probability of an illegal triangle appearing in S. The probability that an illegal triangle appears in S is at most 1 minus P to n/r. This is because we should not sample any of the lines that intersect the triangle. Since there are at least n/r lines that intersect the triangle, the probability that this illegal triangle appears in S is at most 1 minus P to n/r. Similar to the previous video, we can do the following operation, we can do the following estimate. Now we use the estimate that this term here is at most 1/e, which means this probability is at most e to the minus p times n divided by r. Now we substitute the following value for p. We set p to be some big constant times r times log n divided by n. By plugging in this value as p, you see that this probability, the probability that you see an illegal triangle in your cutting, is at most 1 over n to the 7. And now if you count the expected number of illegal triangles, we can get the following bound. This is the maximum number of illegal triangles. Notice that this is an absolute bound on the total number of triangles that we can create by picking 3 vertices of the arrangement P. The arrangement P has at most n squared vertices, and this counts the maximum number of ways we can pick 3 vertices and connect them to get a triangle. This term here is bounded by n to the 6 times 1 over n to the 7 is at most 1 over n, which we can assume is at most 1 over 5, since n we can assume is bigger than 5. So the probability of obtaining an illegal triangle is at most 1 over 5. So this means that second bad event, that the probability that the cutting contains an illegal triangle is at most 1 over 5. You can again think of it in the following way. Since the expected number of illegal triangles is less than 1 over 5, then if at least 1 over 5, 1 out of every 5 triangulation that we obtain here contains a legal triangle, then it would follow that the expected number of illegal triangles will be bigger than 1 over 5, which would be a contradiction. So combining these two facts that we know, we can now conclude the proof. The probability that one of the bad events, one of these red events happen, is at most 2 over 5. Therefore, with probability 3 over 5, none of them will happen. In other words, we'll have n squared times p squared triangles, and we'll have 0 illegal triangles. Note that since p is said to be some constant times r times log n over n, this value works out to be log squared n times r squared, which is a factor log squared worse than the bound we promised, but is still close enough for many applications.